We are proving trigonometric identities. There are lots of them. We're going to see that by the end of the chapter, that there are a lot of trigonometric identities out there. Again, this stuff's been around for thousands of years, so they have formulas built on formulas all over the place. Our proving doesn't mean geometry. It means taking algebraic steps with the trigonometry to lead us to a valid conclusion. That's what we're doing. It is the thinking of geometry where it has to be valid. It can't just be something where we say, oh, I'm just going to do this because I want to. It has to be something that we know is fair game in algebra or trigonometry. So we're going to apply strategies for proving identities. We're going to prove some algebraic and trigonometric identities, and some that don't work, we're going to tell them, hey, this doesn't work. So when we are proving trigonometric identities, we're going to be doing the same thing you were just doing in the homework, but we're going to know the answer. Kind of nice to know the answer in advance. You know what you're working towards. You know, with the stuff you guys had, it was like, I don't know where I'm going with this, but I'm just going to keep going. Here, it's the same thing with algebra. Whatever we do over here, we know has to lead us to 2. It has to. It's supposed to be equal over there. So the proof begins with a left and a right side to an equation, and it ends with us saying, okay, I did all the algebra stuff I can do to this and all the trig stuff, and I got that. Yay me! You know, you made it work, and you showed all the steps that got you there. So the proof in between consists of showing a sequence of expressions, each one easily seen. Notice that. Easily seen. Don't skip steps, or you'll miss major points on this. It has to be something that anybody that knows just a little bit of trig could go, oh yeah, that makes sense. You know, no skipping steps. Easily, each one easily seen to be equivalent in the preceding expression. So, this is algebra. You've done this before. So I'm looking at this and I'm thinking, you know what, I see something we could simplify right away on the left-hand side. I'm not going to try common denominators just yet. This is the difference of 2 squares. That's factorable. I see some stuff that's going to drop out and make this easier. So here's what I do. I'm ignoring the 2. That's not where I'm going to start. We usually start with the more complicated side and try to get the nice side. So x plus 1 times x minus 1 is definitely how you factor x squared minus 1. And then, yeah, they did the subtraction thing, but I want to hang on to that for just a minute because I'm interested in simplifying these 2 fractions. That's what I'm interested in. So let's see. Well, x minus 1 is definitely going to drop out in the first one. And in the second one, x plus 1 is going to cancel out. Now, when you cancel one line, that's all you do. Just put 1 through it so the person that's going through this can see, hey, look what I did. I had it all factored nice, and then I was able to cancel that out. And back here, same thing. Cancel that out, but make it obvious. And in the back, notice I'm leaving that x minus 1 in the parentheses because I don't want to do 2 steps at once. I don't want to distribute the negative and do that. And with these, we really should have equals. With the ones we were doing yesterday, it didn't matter if there was an equals or not. You could see the steps and it kind of followed. But we want to get an answer when we're done with this, and we want this answer to be 2. We know where we're supposed to go with it. So I look at this and realize, well, I do need to distribute that negative now. Done all I can do without distributing that negative. And then I'd want to combine like terms. Well, x minus x is 0, and 1 plus 1 is 2. That's an algebra proof. Step by step, showing, hey, this stands for 2, which, by the way, is super cool. Next math party you go to, Kool-Aid, calculators, and cake. You write that down and say, that's 2. That's cool. Yeah, blank stairs. Blank stairs! That's cool! That is absolutely cool. We got our own secret code stuff going on. I love that. I love it when you have some big monster equation and you get it down to something really basic and simple. Alrighty, proving these identities. We're not going to be scared of the P word. General strategies. Begin with the more complicated expression and work toward the less complicated expression. We did this. tough algebra, we left the 2 sit over there, and we were trying to get to that 2. If no other move suggests itself, convert the entire expression to one involving sines and cosines. We're better at those. And maybe we'll see what's going on if we use those primary trait functions. Not so much with tangent, because tangent we can write as sine over cosine. But if you can't see a move, you try that. Combine fractions by combining them over a common denominator. Yeah, after you do several of these, there's things you notice. Hey, it seems like whenever they're having us put 2 fractions together, the best stuff happens when we get a common denominator. It just does. Or sometimes you look at the denominator and you see it's secant x minus 1. And you say to yourself, if I multiply that by secant x plus 1, it'll be tangent squared, and I can go from there. It's those little things that you keep in mind. So we look at A, and we say to ourselves, okay, which 2 would be the obvious ones to start with? Well, there isn't really an obvious one here, except that addition with trig functions is more difficult than multiplication. So what we would want to do is start over here and think, okay, tangent x plus cotangent x. How am I going to get that? And just kind of ignore. I mean, we know we're going to get secant x cosecant x, but kind of ignore that for now. Well, it's not a fraction, so common denominators are not going to help. I guess I'll just have to change this into sine and cosine and see what happens. So sine of x over cosine of x plus cosine of x over sine of x. Okay. All right, I got that going. With fractions, usually once you add them, you can see something. You know, something magical happens. I'm going to need a common denominator. So let's see here. Let's multiply this one by the sine of x on the top and the bottom. And let's multiply this other one by the cosine of x on the top and the bottom. Oh! You see it? Is something good that's going to happen? Yep. So on the top now, we will have sine squared x plus cosine squared x over cosine x sine of x. Why is that good? There's a 1 on the top. There's a 1 on the top. All right, so now I start thinking towards the end. So I have to make it clear and obvious that this gives me secant x cosecant x. Even the order is important. So I start thinking secant, that's 1 over cosine. Well, yeah, I could just split this and make this 1 over cosine. And then I need that times cosecant x. Well, that's 1 over sine. I definitely have this. It's right there. And now anybody that knows even a little bit of trig can see, hey, that's secant and that's cosecant. That looks like a 5 instead of an S. There we go. Better if you know the answer? Helpful, right? Seriously helpful. This is what I'm supposed to get in the end. All right. Let's look at B. Of the 2, which one is more complicated? Oh, there's an argument for both. There really is. But you know what? What I look at when I'm seeing this is, one of those is factorable. So it would probably be a really good idea to start with the one that's factorable and maybe work my way to the one that's not. This is a difference of 2 squares right here. This is sine of x squared squared. Oh, I better put a couple of parentheses around that. I dropped my equals on this one too. There we go. That's a difference of 2 squares. I mean, it looks a lot different than factoring x squared minus 1. But the principle is exactly the same. we're going to need a sine squared x plus cosine squared x times sine squared x minus cosine squared x. Ding, ding, ding! Prize is right there. Absolutely. Now let's keep our eye on the prize. Does the prize have both sine and cosine in it? The answer. So here's where we think to ourselves, gosh, is there some way for us to write sine as something with cosine instead? Specifically something with cosine squared instead. If you're not seeing it, remember, sine squared x plus cosine squared x equals 1. So we'll use that Pythagorean identity and we'll say, hey, if we need sine squared x, that's 1 minus cosine squared x. And we'll substitute that in there. And do you see the connection? You're kind of thinking, well, where are the 1 and the 2 going to come from? And you realize, oh, it makes perfect sense now. 1, nothing else with an integer there, so that'll be 1. Minus cosine squared x minus cosine squared x is minus 2 cosine squared x. There it is. There's the right side. Well, there's a lot of ways. There's a lot of ways you can do these. What you want to try to do is use the least amount of steps possible. That the word we use for the best math possible is elegant. So you want to keep it as elegant as possible, but definitely more than one way to prove these things. Definitely more than one way. Try to go with what's obvious. You know, if a person that knew a little bit of trig could follow it. All right. Ah! Look at that one. Ooh. Identifying and proving an identity. Oh boy. Match that function with one of those. Yes. Okay, then confirm the match with a proof. Boy, I wish there were some way for us to know beforehand which of those gives you exactly the same thing. It's a good thing we have a graphing calculator. So, you know, we can graph this and see what it looks like, and then we can graph this and see what it looks like. And if it's exactly the same, we know they are the same thing. But these are kind of monsters to punch in. All right, graphing calculator, we're going to make sure you're in radians. That's what we're going to do first. We're doing trig. Oh, anybody need to borrow one? Everybody set today? Okay. Oh, still in radians. All right. I'm going to need parentheses and parentheses to get the calculator to eat that up. So, parentheses. 1 divided by parentheses. Oh man, secant. My calculator doesn't do secant. 1 over cosine. So, 1 divided by cosine of x minus 1 parentheses. I think I got it in there. Bless you. Nope, another set of parentheses. Yep, that's where the problem's going to be, right there. Otherwise, it's going to mess up. Do you guys know how to insert? Anybody ever teach it if you forget a parenthesis or something? If you go to where you want something to be put in place and you hit second delete, it says INS on there so that you could just plop one thing in without having to punch the whole thing in again. So now I've got my cosine x minus 1. Matching parentheses for that. Oh, no, there. That one matches that one. That one matches a short one. There. You still have to do the plus blah blah blah. There's another one. Plus parentheses 1 divided by parentheses parentheses. What do we do for secant again? 1 over cosine. That one in there. Yeah, that's what we're trying to do here with this mess because we don't have secant in there. That's it. And then this one, not quite as hard. Like so. Oops. Hopefully those are the two that are the same, but this one would be much easier to punch in. So my window, negative 2 pi to pi. 2 pi actually would probably be better. And then we just need like negative 2 to 2. All right, first graph. And all we're watching for is, does the next graph even appear? And I can see the little lines over there on the right that mean it's working. Did anything else show up on there? Now, if you want to be certain, you can go into y equals, and you can change your second graph to a bouncy ball over to the left-hand side. So you just keep hitting enter. There's the bouncy ball with the line. And now we'll see the first graph and the second graph will have a little bouncy ball that will come over the top, so we'll be able to see if it's exactly the same thing. Exact same graph. Right over the top. Now, if you wanted to be certain, you could punch in the 1 over secant x, which 1 over secant is kind of silly because that's cosine x. But that one is, it's not a match. It's not going to happen. So to see that it's a match, obviously we needed a ton of parentheses to make this one work. Well, we're not done yet. We just know what we're shooting for now. So it said match the function with one of the following. We would do this. We would say GC, that one. That one. That's the one that matches. So now comes the fun part. We're going to make this, this. So what we have here as 1 over secant x minus 1 plus 1 over secant x plus 1. Somehow, with our magic trigonometric knowledge, gives us that right there. It's a fraction. First thoughts, what would you try? Common denominator, okay? Common denominator. So, I'm going to skip a step. You see anything good that's going to happen when I'm writing this out? Maybe not. Well, let's leave it in factored form in the denominator for a second, then and see what happens. We've got secant of x plus 1 plus secant of x minus 1 over secant of x plus 1 times secant of x minus 1. Now let's see if anything good is happening in our numerator. Is that leading us closer to what we needed? I can't see it anymore because I scrolled up too far. We got the 2! Woohoo! We have a 2. Okay, what else do we need? Okay. Cotangent. Where does cotangent come from? Tangent upside down, right? Well, let's go ahead and multiply those two together. Oh, that spacing would be bad. Secant squared x minus 1. Tangent? Everybody recognize that one? If you don't, remember you write down sine squared x plus cosine squared x equals 1. Divide through by either cosine or sine, you'll get the other two primary trait functions. Okay, let's see if we're closer to what we needed. We needed cotangent x, cosecant x. What do you want to do, Cassie? Move it up and make a cotangent? Up top now. Thoughts? Yeah, I do sine and cosine at this point and say, what on earth do I have here? You know, there's a lot of stuff going on here. So if we have 2, what's secant? Secant. 1 over cosine. What's cotangent in terms of sine and cosine? Cosine? Okay, but this one's squared, so we need cosine squared x over sine squared x. Well, at least one of them's gone. I'm going to write the other one again. All right, so we've got cosine x over sine squared x. Is that getting us to 2 cotangent x cosecant x? We got it if we break it apart? Okay, then let's break it apart. What do you need for cotangent? Cosine over sine? And what do we need for cosecant? Do we have a leftover one? We do. There's 2. There's cotangent. And there's cosecant. Do you suppose if we didn't know that that's what we were supposed to get to, that that's what we would have gotten? Not a chance. Not a chance. We needed to know where to go. You know, we might have stopped right here and said, you know what, that's the best I can do. I've got cosine over sine squared x and called it quits. But we knew where we had to go, so at some point we finished thinking, let's keep pushing forward and start thinking, okay, now push backwards a little bit. You know, this is what I need for an answer. How do I get that? And go from there. The one thing that I remember this homework, because I don't like that they keep bouncing around. They use X in some of them, they use T in some of them, they use theta, they use phi, they're using every symbol under the moon, and really our focus needs to be on just getting these proven. All right. Question? Just stretching.
Stretching.
All right. We had 2 boxes of general strategies so far. Not enough. We need a third. Use the difference of 2 squares, which we already did when we did the algebraic proof earlier. So use the algebraic identity a plus b times a minus b equals a squared minus b squared to set up applications of the Pythagorean identities. You know, if we can use that, we need to. Always be mindful of that target expression, the one you want to get, and favor manipulations that bring you closer to that goal. You know, don't just do things because you look at it and go, proportion, I can cross multiply. Don't do that. You know, we don't do proportions with these. We do one side, work it till you get the other side. That's what we do. So don't be impulsive. So we're proving this little monster, huh? Let's see here. Well, I'm going to start with this side. And you don't always have to start with the left, by the way. But I did that because of what I saw on the other side. Notice my denominator. If I was trying to get rid of that as a conjugate, you know, as that perfect squares that they just showed us up there, that difference of 2 squares, I would be multiplying that by 1 plus the sine of t. Is there an advantage to that? Look at what our answer is supposed to be. There's a definite advantage to that. So if I start with this side and I think, okay, just conjugates, you know, trying to get rid of stuff in the denominator that's not working for me, I would normally do this. So on the top we would have the cosine of t plus cosine of t sine of t. But now that's going to be over 1 minus sine squared t. Oh, light bulb moment. 1 minus sine squared t. Are we supposed to know what that is? What is that? Cosine squared t. Well, now if we can factor at least one of those cosine t's out of the top, we can do a little canceling. See what happens. Oh, when you factored, you get that little tingly feeling? This is going well. We wanted that 1 plus sine of t on the top. Remember, that's what's supposed to happen. We're supposed to get 1 plus sine of t on the top. By factoring, boom, there it is. What do you see? One of the cosines is going to cancel out. Ta-da! Oh. We didn't even get to the complicated one today. Yeah. Yeah. You okay with that one, though? Do you think you would have tried, I mean, if you looked at it for a little while, do you think eventually you would have tried the 1 plus sine t? Would anybody have thrown that out there? Okay, well, at least now you'll know when you're looking at the homework to give it a try. Oh! Man! Oh, you just need that one anyway. Ignore me. Take a picture if you need to. It will be on the completed notes. I'll put it on there during my lunch. It'll be on there. You gotta go. Oh, I don't want to make you late. I'm sorry.